A declaration from educator Carlos, focused on Durham School. I've committed my entire calling to encouraging a specific speculation about the universe. Then this happens. The speculation is being tended to. I embrace this test, since it is through such examining that we advance and gain ground in science. The James Webb Space Telescope is basically disturbing some extended-held convictions in cosmology that have been recognized as truth for a century. Another ultra-trackdown picture has revealed that we have made mistakes in space science. The telescope, which was intended to uncover the chief stars of the universe, is fairly troublesome. The past viewpoint might introduce a completely new, legitimate perspective. Not all experts are grieved about these new disclosures. Various specialists are welcoming these headways, since it has for a long while been evident that there were issues with our past speculations. The abnormalities in assessing the universe's rate of development alone should have raised alarm. In any case, researchers a surprisingly long time ago, instead of accurately unraveling these warnings, many clung to outdated speculation. The infinite microwave background radiation, CMB, which is the most ancient light in the universe, was made around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen particles. This change, known as reionization, made the universe transparent to light. The CMB was first identified in 1964 by American physicists Arnold Penzias and Robert Wilson, while they were working on new radio receiver technology. They encountered a persistent noise coming from every direction overhead. This discovery was initially considered strong evidence for the Big Bang theory. Penzias and Wilson were awarded the Nobel Prize, and their findings became an important foundation in the history of space science. The CMB probably provides a glimpse into the early universe, with microscopic temperature changes offering essential clues about the conditions shortly after the Big Bang. Scientists use the CMB as a trustworthy marker to estimate significant pieces of the material universe, including the universe's expansion rate. Edwin Hubble had already made such assessments in the late 1920s. He saw that distant galaxies were moving away from us in all directions, and that their speed was related to their distance, a relationship now known as the Hubble law or the Hubble constant. Notwithstanding the fact that Hubble's estimates were not as precise as they are today, they were pivotal. When the CMB was discovered, experts recalculated the expansion rate, finding it to be significantly lower than Hubble's initial estimate. Subsequent recalculations using type Ia supernovae as standard candles provided a more accurate estimate. However, discrepancies remained, and the difference in expansion rate estimates has been known since the 1990s. Experts have speculated that there might be issues with the CMB data, analysis methods, or the concept of universal expansion. This divergence, known as the S8 tension or Hubble strain, suggests that our understanding of the universe may be fundamentally flawed. Since the James Webb Space Telescope, JWST, started its operations, it has provided extraordinary data that could help explain the issue. Worlds so old and mature that their formation may theoretically have begun before the Big Bang are testing old scientific theories. Astronomy now faces what is considered to be the greatest crisis in modern astronomy. The expansion rate of the universe and the theory of how things came to be are under intense scrutiny. New images reveal a universe that differs fundamentally from past models. The S8 tension has served as an early warning, with researchers who still cling to old theories now grappling with the realization that our understanding of the universe may be incomplete. This uncertainty has left many investigators troubled and frustrated. To address this crisis, we must understand how science works. Hypothetical scientists use a combination of mathematical models, observational data, and logical reasoning to arrive at conclusions. Their knowledge comes from noticing anomalies, test results, and speculative analysis. The term theory itself implies constructions and ideas, rather than outright facts. Our rational knowledge comes from images provided by telescopes, sound waves, and radiation captured by radio telescopes, as well as data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to break down the oldest light into individual frequencies and analyze it in extraordinary detail. It can show which elements were present in galaxies billions of years ago, the mass held within them, and the number of stars present. However, Webb's images may have limitations. For instance, it can't easily distinguish galaxies or black holes that emit similar brightness due to gravitational lensing. Our understanding has evolved to consider various possibilities as pieces of understanding, often dismissing alternative explanations. New discoveries from the James Webb Telescope offer vital clues that could lead to replacing old theories with new insights. Scientists are currently grappling with these revelations, which seem so extraordinary that finding new explanations is proving challenging. The latest discoveries are shaking the foundations of physics, causing concern among many experts. Physics principles today are still strongly influenced by Isaac Newton's 17th century work. For centuries, his laws of motion and gravity have provided the foundation for understanding the physical world and the universe. Newton's laws work perfectly well under normal conditions on Earth. However, in space, his ideas required expansion, largely accomplished by Albert Einstein during the 20th century. Einstein's special theory of relativity, published in 1905, changed our understanding of reality, showing that the laws of physics are relative to the observer's motion. His general theory of relativity, published in 1915, extended these ideas with mathematical predictions of gravitational anomalies based on the curvature of spacetime caused by masses like stars or galaxies. While Einstein's theories were clear in many areas, he recognized their limitations and sought a unifying framework without success. No scientist has yet succeeded in this endeavor. It is fascinating to consider where the errors might lie. Michio Kaku, a prominent American astrophysicist, proposed that solving this problem could lead to a Nobel Prize. We need to explore what reality might have been misinterpreted, whether there have been misinterpretations of anomalies, or if telescopes themselves might be at fault. Dark matter and dark energy are top suspects in the cosmological crisis. Current models suggest that dark matter and dark energy together account for about 95% of the universe. However, neither has been directly observed or proven to exist. They may not exist at all, or perhaps have properties we don't yet understand. One possibility being discussed is that dark matter's properties might have evolved over time, potentially showing some form of intelligence. Gravity, which should cause attraction through mass or spacetime curvature, has not been definitively shown to behave as expected. Despite the fact that spacetime curvature ideas from Einstein have been validated multiple times, we cannot entirely rule out the possibility that gravity has unexpected properties or that some other effect is causing gravitational attraction over time. Certain characteristics in cosmology and space science have been established as fundamental constants, accepted as reliable largely due to their consistency. Calculations suggest that small variations in these constants could offer new insights into the universe, possibly explaining phenomena without dark energy. It is also possible that our interpretations of light shifts have been incorrect, leading to erroneous distance estimates and galaxy ages. Perhaps our assumptions about the universe's conditions were flawed, or we misunderstood the cosmic microwave background radiation. It might even be that the universe doesn't originate from a single starting point, challenging the theory of the Big Bang. Small errors in the Webb telescope or other observational devices can't be ruled out. Experts and scientists acknowledge that mistakes in instrumentation, data handling, or interpretation are always possible. The ongoing reassessment of cosmological theories highlights the essential nature of scientific progress, the ability to adapt and advance our understanding based on new evidence. The James Webb Space Telescope's observations are more than just a technological leap. They represent a significant moment in our journey to unravel the universe's secrets. As we wrestle with these revelations, it is essential to recognize the broader context and implications of such logical shifts in the realm of cosmology. The method involved is often driven by the need to refine theories in accordance with new insights. The discovery of strange anomalies or inconsistencies in established theories can be unsettling, but it also presents an important opportunity for scientific advancement. Hypothetical models in cosmology are developed to provide a clear framework for understanding the universe's origins, development, and evolution. However, as new data emerges, these models must be tested and, if necessary, revised to accommodate new insights. One major area of focus is the nature of dark matter and dark energy, which are essential to contemporary cosmological models. Dark matter, an invisible form of matter that does not emit or absorb light, was proposed to explain discrepancies between observed galaxy rotations and the mass predicted by visible matter alone. Similarly, dark energy was introduced to account for the observed accelerated expansion of the universe. However, despite their critical roles in current models, both dark matter and dark energy remain elusive, with experiments on Earth having so far failed to definitively identify them. This has led researchers to explore alternative hypotheses and potential explanations. The challenge of understanding dark matter and dark energy is compounded by the vast scope involved in cosmological investigations. Observations of distant galaxies, the cosmic microwave background radiation, and other grand phenomena provide indirect evidence of these components, but their exact nature remains elusive. This uncertainty has prompted scientists to consider a range of theories, from modifications to existing models to entirely new principles. Some hypotheses suggest that dark matter could be composed of more exotic particles than previously thought, or that dark energy might represent a new fundamental force. Another intriguing area of cosmological investigation is the study of cosmic inflation. This theory proposes that the universe underwent rapid expansion in its earliest moments, leading to the large-scale structure we observe today. While inflationary theory has successfully explained many aspects of the universe, like its homogeneity and flatness, it also raises questions about the nature of the inflationary period itself. Observations that challenge established models of inflation could lead to updates in how we interpret the universe's early history. Finally, the search for extraterrestrial life remains a driving force in space exploration. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up new avenues for studying the conditions necessary for life. Advances in telescope technology, such as the James Webb Space Telescope, enable us to analyze the atmospheres of these exoplanets for potential biomarker signatures. The possibility of finding life beyond Earth has profound implications for our understanding of the universe and our place within it. In conclusion, the reevaluation of cosmological theories in light of new observations is a testament to the resilience of the scientific method. The James Webb Space Telescope and other advanced observational instruments have provided remarkable insights into the universe, prompting scientists to revisit and refine long-held theories. This process of continual inquiry and revision is essential for advancing our understanding of the universe and addressing the fundamental questions that lie at the heart of cosmology and space science. As we continue to explore the universe, we remain engaged in a quest for knowledge that not only seeks to answer key questions, but also inspires future generations to push the boundaries of human understanding.